So hi everyone, I'm Cedric. I'm a PhD student here at the University of New York. I've been using Julia for my work and research for a couple of years now. And at the time I started my PhD, I started doing propaganda for Julia instead of MATLAB. And so eventually the guys at CISM asked me if I wanted to do that for them officially. So welcome to this session on Julia for high performance computing. So on Tuesday, there was a session on the basics of Julia. I only be reminding just like a tiny little bit of that section, essentially the most important part. And then everything else is going to be practical. How do you use multi-threading, distributed computing? So various things you might want to do in Julia, especially running it on the cluster. So also on Tuesday, I started my presentation by mentioning like interesting anniversaries on that date. And interestingly, so on the 16th of November, there were 2 space launches, or actually 3, but I only kept 2. So the Venera 3 launch, the Soviet probe that they launched in 1965, I think, and it would be around Venus. Last year we had the Artemis 1 launch, which is like the renewal of the US space program. And perhaps more interestingly for today, it's also the birthday of Jean Amdahl, which is famous for postulating the Amdahl law in parallel computing. So because we're talking about parallel computing today, that seems interesting to mention. Okay, so I've already showed you the QR codes. Hopefully you have the notebooks at hand. So the rough outline for today, and can't guarantee that we'll be lasting 3 hours. I've been a bit sick and a bit tired, so we'll see what happens. I'll start with a very brief recap on multiple dispatch, which is like the main mechanism of how Julia operates, and especially operates now when it's fast. And then I'll cover some various things that are important in Julia in general, but especially if you're trying to run Julia on a cluster. So we'll start with benchmarking and profiling code, performance tip. Like I will go from easy stuff to more esoteric. I think you can actually say sorcery that you can cast on your codes to make it faster. A quick little interruption on interoperability with other languages, because you might want to call some Python or Fortran or other code that is not in Julia. And it's actually super easy, so I'll be mentioning it a little bit. And then the last part will be about parallelism. So both in the standard library for multi-threading and distributed computing, and then various packages around this base. Okay, any questions, comments? Okay, so let's start with a reminder on multiple dispatch. So one of the big differences between Julia, for example, Python, more so MATLAB, is that Julia has a very sophisticated type system. So here is an example of a slice of the Julia type system. At the bottom, we have what's called concrete types. So these are types that you can use at runtime. And they correspond here to actual memory allocated in the processor. For example, I have stuff like float 64, so double precision floating point numbers, float 16, float 32, big float. Those are all types that you can use at runtime. And you can see that they're all children of this node called abstract float. This is not a concrete type, this is called an abstract type. An abstract means that you won't see it at runtime, but Julia knows that all of these types are subtypes of this. So there's a subtyping relation a bit like in object-oriented programming, but the resemblance stops here. And then there's a whole hierarchy of it. You can see that floats are supposed to represent real numbers. And so that's represented by the fact that it's a child of the abstract type real, which represents real numbers, and other types included would be integers, unsigned integers, and so on. And then above that, we have numbers, so stuff that you can add and multiply and so on. So, for example, there's complex numbers. Question? So we have complex numbers would be a subtype of number, but not a real. And then all the way at the top, we have the any type, which is basically the type for any type, so just arbitrary types. it's necessary in the type system to have this, but if you at any point you see any type in your code, or especially code that you run, you should be worried, because that means your Julia program is basically running as if it were Python, because it has to do a lot of checks around the types at runtime. So a big deal about in Julia is really having this hierarchy of types to help you work with and structure your program. But then at the end of the day, when your program runs, it knows exactly what the types are, and so it uses those on the bottom at the end. And the second ingredient is that's called multiple dispatch, which I can summarize as saying that functions in Julia can be overloaded. So I can define a new version of a given function. That new version will be called a method. And I can do that depending on the type of all the arguments in that function. So for example, this is a shorthand definition of a function in Julia. I can define my function foo, which taking an x, so x is inside, this means foo for x of any type. And I can say, okay, that doesn't look like a number. But I can then restrict, if foo is a subtype of real, or x is a subtype of real, so then for all real numbers, this will use this definition to print, oh, now I've got a real number. But then I can specialize. Notice that I took an abstract type. I'm saying for all subtypes of this type, do this, unless there's a more specific definition I use later down. So integer is also a subtype of real. But here for integer, I've overloaded the definition, saying if x is a subtype of integer, please print me got an integer. And then I can also do that for a very specific type. So int 64-bit signed integers, that's a concrete type for this specific type, and saying, please give me a 64-bit integer.
Is the order of the definition important?
Nope.
Or the most specific?
Like, it's only the most specific. So whenever the Julia compiler has a call, it's going to look for the most specific method defined. So the order of defining these doesn't really matter. But you could think of this as a kind of pattern matching on types. You could almost do this with like a switch or a case statement. Okay, so that's for one argument, but actually you can do that for arbitrary number of arguments. So for example, I have a function that takes 2 arguments, and I can do just the same of specifying the result depending on the results of both the type of both inputs. For example, let's have 2 real numbers, 2 real numbers. You can also do some more specific things. For example, if I want to specify that both types are the same, I would do something like this. So bar t, y, t. And t, you can think of this as like a type variable. Then I have to qualify it to where t is a subtype of real. So this definition will only apply whenever I call the function bar with 2 objects of the same type, and that type is a subtype of real. So for example, if I were to call this something like a float 64 and a float 32, they would not be of the same type, and so this definition would get used. Yes? So you could specify that the return type is t in this case, for example. So you can always specify the return type, and if you have captured the type variable, you can return t. But in general, the return type of a function in Julia is not, you don't have as much control on that. But we'll see examples of that later. So everyone clear on that part? Yes?
The fact that the example where it's not that equal sign.
That's the type. Sorry, I knew. There should be an equal here, but I forgot it. Okay, so there are some gotchas with these like type parameter or type variables. So last time I talked about parameter types. So in Julia, you can define new types, and this would be an example of specifying the type with here supposed to represent a point to 2 components, but I want to be able to be flexible on the actual type of the coordinates. And to do that, you use what's called a parametric type. Here, again, a type variable t here. And then the fields of my struct are of that type t. Now, an easy mistake to make when starting to learn Julia is to try to define a function like this. So let's say here I want to take a vector of points and I want the center. So ideally the mean or the geometric mean. And you might try something like this. So I take a vector, so a one-dimensional array of points and of element type real. But if you were to try this, this would not actually work. The reason is that the vector points to the real is different from point to the, in this case, we have a subtype of real. So there's a distinction between this type, which means I have a point 2D and this t parameter is real, and point 2D where I have a subtype of real. So remember, you can only have a concrete type during runtime. So this one does not really make sense. So if you wanted to say, give me the center of a vector of points such that they are subtype of real, this should be what you use. With a bit more explanation here. It's about really the type of elements of a container. So this first type is the type vector int. It's a vector of integers, specifically 64-bit integers. And this, for example, you could use in a function definition. So if you were to define a vector t subtype of real where t, this means I want a vector of element type t. So there is a definite element type where t is a subtype of real. And a shorthand for this is this. You could say either this or even this one as a very shorthand if you don't care about naming t. And then vector real would be a bit different because it could be a vector of different objects. They don't have to all have the same type, but they just have to be all subtypes of real. So if you somehow manage to get a vector with an integer, a rational number, a float, and they would stay different, that would be a vector real. And the Julia compiler would not be happy about this because it does not know how to, because these are different types, different memory layouts. The Julia compiler has less of an easy time of storing that in memory and optimizing code. So keep this in mind that this is slightly more advanced. Okay, so I now start with my first example. Close it, sorry. So first little notebook. Now this is very small. Should I increase the size here a little bit? Maybe. I think I probably should, yeah. Settings. A little bit better. So I need to add the Julia kernel. So I'm starting fairly nicely here with just basic tools in the default standard Julia library on how to optimize or inspect the quality of the code, especially how it performs. And so let's say, for example, I define a very simple function, foo, and I can call it on an integer, so fine. There is a bunch of these, so at things. In Python, you might think that those are decorators. In Julia, those are macros. So a macro is really a thing as a function that takes a Julia expression and modifies it. For example, the macro code lowered foo is going to look at that foo and is going to write the generated code by this. Look at this. It gives you essentially a list of the, not quite the low-level instruction, but almost. It says that, okay, I'm calling this function for this type, and then at this expression. So it's whenever you want to inspect the code generated by a given function call, and there's others. So a nice variant is code typed. which also give you type annotations on the different steps. It's maybe useful if you're trying to make sure that it's a specific type that's being used. And more useful, in this case, there's no problem, but there's the macro code warp type. What it's going to do is whenever, if your code has any points where the type is ambiguous, it's going to like write it in yellow or red to tell you that something bad is going on. So it's a very useful tool for debugging. You can even look at the, not quite the assembly, but close enough, because how Julia works is that it works with the LLVM compiler, which is like a bit of a step slightly above assembler, generated by most compilers. And so this is almost as if you were looking at the generated assembler for the code. So you can see here, it's only 3-4 instructions, so not a lot. This also tells you, okay, if you do this step and you have a large number of instructions, that's also a sign that maybe something is wrong. Another, maybe I should go back to the slides. I'll go back to that just a bit later. So another performance tip is when you want to modify an array. So let's say I have this function that's going to take an array, A, and it's going to write something to it. Notice that I put an exclamation mark at the end of the name. That is not mandatory, but it's a convention in Julia that whenever a function that modifies one of its arguments, it should have this exclamation mark to denote that it is in place. And usually using these in-place functions is an easy way to gain performance, because among the things that can take a lot of time during your program is allocating memory at random time. So it's usually better to allocate memory at the beginning and then modify it. Yes? In a sense, yes. It's as if it were a pointer. But there's some little trickiness with that. So you could call this on a vector, so let's try this. So x is equal to 5, so just a vector of type. I could just set a random vector, and I can call in place x, then display x again. So I've called that function, and you can see that, maybe not super clearly, but the elements have been changed. Not a lot, because the difference that it does modify at least a vector in this case correctly. But then you might run into trouble if you try something like this. So let's say now I have a matrix, 5x5 matrix, and I want to apply the in-place function to each row of A separately. Of course, for whatever reason you want to do that, it's useful, for example, with OSD code. So you could try this, but you'll find that it will not work. The reason for that, so yeah, so I've tried this loop, didn't change anything about A. The reason for that is that this indexing A, so AI dot, so that's a slice of A. In this context, it creates a copy of A. So the in-place function gets called on a copy, but then the copy disappears. So the actual array is not modified. So the way to do that properly is to use what's called a view. So a view is really this idea of almost like a new array, but it's really looking at the same part of your array. So say you want to just look at a given column of the matrix A, get a view, and this behaves as if it were just a one-dimensional vector, but it's still the same memory. And so when you modify the view, it will modify the actual array. So to do that, use the view function. So view works a bit like the same. So you take view, your matrix, and then the indices. So because I wanted I dot for the whole line, I use that, and that works. Now, this might be cumbersome, especially if you have a loop with a lot of stuff. So there's a really nice macro for that, called the views macro. It's another macro, so it's going to modify this loop. And what it does, it looks at a block of code, and whenever there's an array indexing operation like this, it's going to replace it with that view function. So it's just a shorthand. So views applies to the whole loop, and whenever it sees an indexing operation, it replaces it with view. And it will do that for every indexing operation. So it's a nice way to make your code a little bit easier, while also more performant. Okay. And there's a whole bunch of stuff like views all over the place. I think, yeah, we can keep going on this part. So I mentioned something about abstract types being something you do not want to see at runtime. Another thing that you want to do is something called type instability. So, Julia, a function states that to be type stable if the output type can be inferred by the compiler just based on the type of the input. It's better to explain with an example. This following function is not type stable because the actual type of its output depends on the value of its input. So notice that here, if x is smaller than 0, I return a string, but otherwise I return x. So if x is a floating point number, then depending on the value of x, which the compiler cannot see, it's going to return either a string or a float or a number. So this is what people mean by type instability, is what you cannot really determine what the output type is going to be just based on the input types. Now, this is where the code one type macro is very useful, because it's going to find that problem and highlight it for you. I can call code one type on my function type stable on 1. And you see here it's highlighted in yellow. It says this type here is a union of int, 64, and string. So it does not know whether this is an int or a string. And so this is an indication that there might be a problem in our code. Now, this is a bit more of an obvious example, but see, it seems to be more solved. So look at this function, value, that is fairly common in machine learning. The idea is this function that if x is smaller than 0, it returns 0, and otherwise it returns x. Now, I claim that this function is not type stable, but I'm curious if anyone has any idea why. I think the 0, here it's a constant. And specific, it's a constant of type int. So it's sort of the problem here. So this is a ternary operator, I can see. Right? So it checks a condition. If true, it does one thing. If false, it does another thing. And here, if x is smaller than 0, it returns a constant 0 of type int. So it's always going to be 0 of type int. Otherwise, it returns x, and x might be, it's going to be whatever the type of x was. So that's one subtle way you can generate a type unstable function. And you can see that by trying to, like, a value on a float of value 1 in a float, and on -1, I get an integer. And if you go code one type on this, again, it says there's an ambiguity. It's not sure whether the value is going to be a float 64 or an int 64. So how to fix this? Luckily, it's very easy. So if you want the 0 of whatever type, you can use the 0 function. And so you just replace the 0 integer on top by 0x. And what 0x is going to do is going to return the 0 value of the type of x. And there's also a function for the 1 version of, or give me the nearest value of the same type. So take y and give me the nearest value of the same type of x closest to 1. Now this function is going to be type stable because the type is always going to be the same as the type of x. We can look at it, let's use a code one type, and indeed there's no more ambiguity. Okay. Another mistake that's fairly easy to make is when defining structs. So sometimes you might see people defining struct like this, where they don't define the types of all the fields. That's a terrible idea, because if you define your struct as this, so there's an x that has no type, so implicitly this means the type is any. And then you say, okay, maybe y should be a subtype of real, so I'll try doing this, saying y is a type real, and z is a vector of integer, so stuff that is a subtype of integer. Maybe that should work. Unfortunately, this will not. For the same reason I explained earlier, when you create an instance of this type, Julia has no information about the actual type of x, the actual type of y, the actual type of z. It just knows some bounds, so we can maybe try and constrain the memory, but it's not exactly sure about what the type is. So you should not do this. What you should do instead is specify precisely the type of each field using parametric types. So the proper way, it's a bit more verbose, would be something like this. So I'm saying foo, good foo, has 3 type parameters, t1, which has no bounds, t2, which should be a subtype of real, and t3, which should just be a subtype of integer. And now I can say x is of type t1, y is of type t2, z is of type vector of t3. And now when I create an object of this type, these types t1, t2, and t3 will be part of the type. So all the information about what's going on in this object is going to be available to the compiler. Okay. And then I think the last example is more about how bad is it to have abstract types or abstract field types at runtime. So let's define a structure. Here it's mutable, so I can change its arguments. It's going to have one type parameter, t, which is going to be a subtype of abstract float. So far, so good. And I'm going to define a function foo that increments a by 1. This is a well-defined function. It's very interesting to compare the LVM code. So remember, it's almost the same as the assembler. And here it's the function version of this macro. So you give it first the function and then tuple with the argument. So this just says what is going to happen with this function when the type of input is float 64. And here we see that it's again just a couple of lines. So because it's only a few lines of essentially assembler, this is going to be a fast function. On the other hand, if I ask, okay, what should it look like when the type is abstract float? So you could not get this at runtime, but you can at least ask the compiler what it would do. And you can see that it's a lot much more code. And all this extra code here is just essentially bookkeeping to check, is this type various things about the type, because it's not sure about the actual type of its input. So since this is essentially assembler, the more instructions you have, the more time this function takes. Long story short, make sure you're in this context and not in this second context. Which, by the way, this behavior is basically how Python works by default. Unless you do some voodoo magic, but the default Python is going to be that. let's go back to the slide. So I'll go through the slides a little bit, but then all of this we'll see in actual examples a bit later. So bear in mind, so if you want to measure the performance of your code using benchmarking, so there's again a few macros for that. So on the left, you have macros that are available in the standard library. For example, give the time. So time foo. So take time a function call. This just measures the time it takes for foo to execute, and it's also going to measure the memory allocated. Maybe if there's a garbage collection, so it's going to give you a bunch of information about how much resources this call took. And then you have variants if you only want the time or only wants the memory allocated and so on. Importantly, this one, it's only going to measure a single call. So if you want to do some statistics, this will not be very precise. And also, and we'll see that in a minute, due to the way Julia code works, the first time you call a function, it's going to be a little bit slower because it needs to compile it. The second time, the compile version will be already there, so it's going to be faster. But that's something to watch out for, that the first time you do a time, it will be an overestimate of the actual time of the function because it has to have to do all these compilation steps. Now, if you want to do some proper benchmark, you should really use this package called benchmark tools, which defines a benchmark macro, which is going to do essentially the same as time, but it's going to run through a certain number of time, ideally tens of thousands. So it's going to run through a bunch of time to get some statistics, especially at the end, it gives you what is the average time it took, the standard deviation, the median, and so on. And again, you have variants if you just want the time or only some statistics. Okay, so this is for profiling. I have an example that this is much clearer, but sometimes you have a function that's very complicated and you want to see, is there any specific part of the function that takes a lot of time? For that, you would use a profiler. Now you have a built-in profiler using profiles. This is part of the standard library. You don't need to install this package. It's installed already. And then it's a bit like time, you do profile foo. And it's going to give you a few informations, but it's only going to be in the repo, so not super useful. Luckily, there's a bunch of packages for visualizing the profile. So I have two here, but there's more. So one's profile view and one's dprof. Dprof being like a tool by Google. We'll see them in a minute. It'll be much clearer. Also, note that here, every time on the bottom, I'm noting the relevant part of the Julia manual. So you can use this for reference later. Okay, so I think I should probably step. That's some profiling. So this is an example of profiling code. So roughly, I have a big function here. It does a bunch of operations. You can see that it creates an array. It computes a function of that array, multiple functions, does some slides. So it just does some stuff, and it does that in loop. So I'm going to start a Julia process in VS Code. So you can see on the bottom, it starts out a Julia repo. And it loads the package over here. It's going to load the profile package. Okay, so it's loaded both dprof and profile view. So I can define a function. I can call it on like just size one just to compile it once. So now it's done. And then let's look at how profile view does it. So profile view is going to normally make a GTK. We get a little window that appears. And this is a flame graph. So I can inspect each part here. I can see, oh, it's this part of my function. It's not super clear. So this is maybe not super useful, but you can do a bit more of this normally. So for example, this tells you this is the source. It took some time. So roughly, this gives you some information about in that function call what took some time. Now, I generally prefer pprof. So pprof is a bit different because it's open something on your browser. Should have opened. Okay. What pprof did is that it opened a server. So let me. Okay, so it's opened a local website. And here I have a bit more information because it gives me a whole graph of all the calls that were made. Unfortunately, I cannot zoom here, but if you zoom in, it would say, okay, this is this function, it looks this much time, and so on. So if you're trying to see, optimize a program, say a simulation that does some processing, and you notice, there's this dumb operation that takes a bit of time, you can look at that and optimize it. Also the frame graph. But here there's not that much interesting to say, but so various ways of profiling a program, whichever you like. This is probably something that you'll find enough. Okay, so that was profiling. I think I wanted to do something about performance. Yes, here. Okay, so I'll do all this time. So yeah, so more performance tips. So here I'm basing myself on this part of the manual, which gives you the different tips and gotchas and things to avoid. I already mentioned a bunch of them, but maybe the most important is put your code in functions. The Julia compiler is only capable of doing its magic on a function call. So any part, like basically don't write a script with no functions, put everything in the functions and then call those functions. That way the Julia compiler can do some stuff, otherwise it cannot optimize scripts. Also, so I mentioned this already, pre-allocate arrays and use in-place functions, because allocating memory in the middle of the program is something that can slow it down, so it's usually better to just do a big allocation at the start and modify memory. This should be true regardless of any language. Global variables are evil. Use const if you have. So const is a way to define a variable as something that will never change in the program. And that way it's a bit safer. Use multiple dispatch to break up functions. So really, whenever you can use multiple dispatch, use it. And sometimes you'll find yourself using big blocks of ifs and conditionals in a function. Usually there's a way to break that down using multiple dispatch. And actually, there will be an example of it. Another one, this one is a bit more esoteric. So the way Julia stores array, it's the same way as Fortran, which means if you have a matrix, it's the columns that are stored first. Why is this important? It's important because whenever you're traversing an array, and a matrix is at the end just an array, it's faster to do it element after elements that are neighbors in memory. And so because a matrix and generally arrays are stored by columns, you should redo, okay, first column, second column, third column, etc. And that will be faster than if you were to do the opposite of by row, for example. This would be much slower because the processor cannot optimize as much your memory codes. And also, I already said, abstract types at runtime are the devil, so avoid them at all costs. Talk about the reviews, type stability, it's fine. Some final comments about squeezing even more performance. So some of these are maybe not so recommendable in the sense that there's some danger entailed, but not all of them. But yeah, you should use these if you have a program that's already well optimized. You just want to get a little bit more performance if you can. The first one, if you have like a program that operates on a small array, like maybe 100 elements maximum, and the size is not going to change, you can use what's called a static array. And it's basically just an array that's allocated on the stack, so it's a bit faster in memory access. So that's one easy way to get a faster array using that, but it only works for very small arrays. Other things like if you want to tell the Joule compiler that maybe try to inline a function, you can use the inline hint. Although a lot of the times the compiler is smart enough to do that on its own. Yeah, these later ones are a bit more questionable. You have a macro called inbounds, and we'll see example of this later, don't worry. So what inbounds does is that it disables the bounds checking on an array. So normally when you index an array, there's a little part that checks that the index you're trying is within the bounds of your array, and there is an error if it's not. Inbound does not. So inbound removes that step. That means the program is a little bit faster because there's a bit less code to run. But you have to be sure that you're indexing correctly. Otherwise, you get a seg fault and your program crashes. So use that if you know that it's safe to do, but don't abuse it. Another slight abuse is the fastmath macro. It's basically going to use faster floating point optimization. But the catch here is that the actual result we get is a bit different than the standard. So again, if you want to remove bolts to get a bit more speed, you have tools, but use them at your discretion and risk. Finally, and this one actually might not need to use it all that much because, again, the compiler is smart. Some processors are capable of doing, for example, vectorized operation. They can do, for a single instruction, they can sort of operate on mini vectors of data. So if I might do a plus of 2 vectors, maybe I have a loop, and one CPU instruction is going to actually act on 4 elements of my array. So that's called single instruction multiple data CPU instructions. And in Julia, you can tell your code to actually use those. But then by default, it could. And finally, this one might be more important if you're running on a cluster and you have a big package that you don't want to recompile every time. You can use something called package compiler.jl. It basically allows you to create precompiled artifacts of Julia code. That means it be compiled already, so you don't need to recompile it again on startup. A lot of people use that to, for example, they want to be able to plot things very fast. And so they will create a compiled image of the plots package that will load instantly instead of having to wait a couple of seconds. The catch here is that you create this version for one version. If you update, you need to create another. Okay, that was various optimization things. And you got the on or not, so it's fine. So I have one small little interruption before getting into the distributed computing is how to call C and also Python and R in Julia. So that's actually very easy. This is also relevant because you might not want to rewrite everything in Julia for a program. And especially you want to be able to use this old C or C++ library without having to rewrite it. And luckily, that's very easy. So for example, you can natively call C and Fortran functions with the C call macro. I'm really only giving like a tiny example, but there's a lot more here. So you can like call function with a compiled binary of C or Fortran. There's some subtleties, but here I'm just calling the clock function from the C standard library. And the way it works, I'm using C call, the clock function. So this should be a C function. And then importantly, I'm converting to the int32 type. Because this step is important because I need a well-defined type, and otherwise this might be the equivalent C type. And Julia also has notion for C string, C int, and so you need to make this distinction. Yeah, that took a bit of time just to call a C function, but that should be faster the next time. Let's actually check. So if I rerun this, you can see that now it took 0 seconds. So this 5 seconds wait were because it had to compile a bunch of stuff. Yeah, you can do that. So you can look at the manual for that. They give you explanation how to call a specific library or just a binary that you have here. There's also some topics about calling Fortran, because Fortran compilers usually mangle the names a bit, so you have to take some care. But yeah, any C compiled C library can call it. Yeah. So C++ is a different thing. There's package for calling C++. Yeah, so this is mostly C and Fortran. C++ is a bit separate. So yeah, I have just two examples of calling two different languages. So maybe you're not happy with the available libraries in Julia and you want to use this Python library that you really like. Luckily, that's very easy and also very seamless. So one way to do that would be to use the Python call package, which, as the name implies, is to call Python code in Julia. There's another one called PyCall, which is a bit more finicky, but it has some nice features. So both are worth checking out. We'll use Python call here. Let's say, for example, I want to import a specific Python module, in this case, the regular expression module. I can just do this one, so PyImport, and then the name of the Python module, and it's going to give me an object. And this will work just like in Python, so no array is the Python module, and I can pretty much use it exactly as if I were using it Python. For example, the next line, I'm going array.final, so this is a Python function final, and I'm giving it a Julia string for the regular expression, and then a string to slice. And notice that here the output says this is from Python world, and the result is this Python object. And then I can also do some more Python operations. So here I'm creating a Python string, so taking a Julia string and sending it to Py to create the equivalent Python object. And then the join word, which is the Python equivalent. So basically, I've taken a string, split it into parts using a Python function, coupled it back together into a Python string. Then we can also get back a Julia string using the PyConvert. PyConvert takes a Julia type and a Python object, and now I have a string from Julia. I have another example that's a bit more interesting, but it's using the old package, but if you want to see it, let me know. But in general, you can do this kind of wizardry fairly easy. Now, maybe you wanted to do the same for R. Maybe you have a specific statistic function from R and you will not find it in Julia. You can also call rcode. So that's using the rcode package. You can see it takes a bit of time to load as well. And here, let's take a Julia vector of rands. So this is a Julia type. And I'm going to send it to an R function. And the way we do that, we write R and then a string. And it's a bit of a convention also, I think, in Python to have like specific strings or special strings. So this is essentially what's hidden underneath here is a macro. It says, take this string and interpret it as an R program or some kind of R code. So here in my string, I'm calling a function from R, t.test, and I'm interpolating my X variable, which is a Julia table in it. And the nice thing is that rcode is smart enough to see, oh, okay, this is a Julia, Julia vector. I'm having to send it to an R function, so I need to convert it to the proper type. It will do that for you. So if I run this code, it's actually run the function from R on my vector from Julia, and it has sent the Julia vector to an R vector. So that's good. And you can also, of course, recover the other way around. This is another example of calling just arbitrary R functions. So here I'm calling empty cars, just a data set. of cars and statistics about them. And you can call just R functions on that. So, I think you can see that it's very easy to just call these languages. And of course, there's packages for calling Julia from Python and R as well. So it goes both ways. But yeah, the feature I like the most is this one about just taking a string and interpreting Julia values and just having that automatically work. There's not that yet in Python call, but there was in the other package. So it's why I like the old Python package, because we can just have a block of a string that just a Python program interprets some Julia values and it works. Like that. When our Python you've seen that. So we can move on to distributed code. Any questions so far? So again, I'll be quickly moving on to, I think, we'll go directly to a notebook for this. So I mentioned we were looking at an example of benchmarking. So this will be more of a like synthesis of what we've seen before, or at this point. It's like the Julia kernel. So here it's actually a full example of defining a function for metric multiplication and trying to get as close as we can to the default metric multiplication in the standard algorithm using various optimization tools. So if you look, the first cell here is just for installing packages if you haven't them already. Otherwise, you don't need to run this a second time. So we can start by defining this function, simple mode. Notice that it's also a in-place function. It takes three matrices C, A, and B, and it's going to replace, do the update, in-place update, C is equal to C plus A times B. So the important part is A times B, it's a matrix multiplication, gets written into C. So maybe you remember how to, the formula for matrix multiplication, or maybe not, but it's very simple, it's just a loop. And then it says Cij is equal to the sum of Aik plus times Bkj. Do that over K. Notice here, I have a triple loop with three indices, but for those who were there on Tuesday, Julia has a nice syntax for fusing these loops into one. So this is really a loop over three indices, but you don't need to do for I, that's done, then do an indent for J, another indent for K. It's just a simple loop works. And we can check this works. So take matrix size 56, take random A, B, and C. And we'll use the time backcode that I told you about earlier. So here you see it says that it about 0.6 seconds. And it also tells us about how many allocations there were and how much memory and so on. So here you can see it says about 11,000 allocations and so on. And 1.52% compilation time. So remember, I said the first time you run a function, it has to compile it. So this is why it's not a good estimate of the time it takes the function. So if I run it a second time, now we can see it took about 0.3 seconds and there's no allocations anymore. So all of these allocations, they were for the compilation process, but they're not part of the actual function. Okay, so now it's fine enough, you just want to have like a simple ID with performance, but really we want to be able to benchmark this. So let's use the benchmark package. And then we can call benchmark as if we were using time. And benchmark under the hood, it runs this function a bunch of times. Might take a couple of seconds. But then at the end, hopefully it's going to be very soon. Yeah, so it's done. notice that it gives us a lot of information because it tells us what was the minimum and maximum, was the median, average, and standard deviation. And it also gives us a nice histogram of the time it took. And it also tells us how much memory was allocated. Generally, you want this to be 0. Here it's the case, so we're fine. So, yeah, I think this estimate here is no longer accurate because for right reason, but here it's more maybe 40 milliseconds per iteration. And we can actually compare with the equivalent standard average. The standard library equivalent function would be null from linear algebra. Null here, it's the same function as before. That is the standard one, and under hood it should go to map actually. Let's try. Now we see that we have about 440 microseconds. So it's actually much faster than the previous function. I don't think it's 20 times faster, but it's much faster. This one. Some amount of time faster. Now let's optimize this function a little bit. So a first thing we can fix is actually, remember I mentioned that it's important to go over an array in the correct order, and here the loops are in the wrong order. Because if you look at this function on the top, you can see my first is over I, so over the rows, then over the columns, and then finally over K. Here, ideally, we should be using J in the first loop, and that should be a little bit faster. You can try that. So here I just swapped going over J first, then over K, then finally over I. I can benchmark it again. You see now we went from about 40 milliseconds to 15 milliseconds. So that didn't happen. So that did make a big difference. But we're still pretty far from the very optimized library. Let's keep going. I mentioned if you know exactly the indices of your arrays and they're correct, you can use inbound to disable the index checking. So let's do that. So we put inbound in front of this expression. That means that it won't check that the ij and ik are valid indices for these three matrices. Let's try that again. Okay, now we're down to 3 milliseconds. So that actually did quite a lot. Maybe there's some other program running on a computer, but right, we went from 40 milliseconds to 15 milliseconds, and now all the way down to 3. So not bad. But can we do better? One way would be to try multi-threading. Now, unfortunately, you cannot start Jupyter notebooks in multi-threaded mode. I tried and I couldn't. So for that, we'll go look at this example. So this is just a program for the threaded version. So the idea of threads, and we'll go back about that in the slides a little bit. For a simple loop like this, you can just slap this macro here, threads. But you need to actually call Julia with threads. So let me open up the terminal. So here So if you want to run Julia with a threaded mode, so I've given a number of threads, you use the call Julia, then you give it the option threads equal and the number of threads. So here let's take 4 threads. Okay, so now I can check that I have any threads. So here it's telling me, okay, I have 4 threads. So now we can try and call this script. So what I'll do is that I call function include. Example threads. So what this will do, it will load this file and it will execute the content of it. So first it will load, so define this function, then it will do what's on the bottom, so define its matrices, loading benchmark tools, and then doing benchmarks. So when I do that, I have to wait a little bit, but eventually I'll get the result from the benchmark. Hopefully not too late. Okay. So we now have an estimate. So it took about 1.4 milliseconds, so a bit faster than even the inbound. Nice, but notice that now we have some memory allocations because multi-threaded code is not free. There's some overhead to do this. And so it's in some circumstances, it might be just faster to use a non-multi-threaded code. So far, we're about 1.4, so maybe you can keep that in mind. Go back here. We can skip this section because you've seen it already. Interesting. Can we do better? Right, we're still a bit far from the optimized version. So the last one is using a package for loop vectorization. What it does, basically does black magic to your code. I think among other things, it uses these SIMD instructions we can. It optimize a lot of things about your loops. But as far as you should be concerned, it should just be this macro turbo that you slap in front of your loop, and that should be faster. So let's try that. Notice that both for threads and this turbo macro, you can only do that on one loop. So notice that here I have to separate my outer loop from my inner loop. That's because turbo really only works on one loop. It cannot really optimize multiple loops or multiple nested loops. Let's see what happens now. In previous time, the last time I tried this, I actually got it to be a little bit faster than the standard library mode. Although yesterday when I tried, it wasn't. So I think they improved the default open task. So now we're about 700 microseconds. Right, so we're getting very close to the default library. Let's see what it was. The standard library was about 400 milliseconds, or 700, so close, but still not quite there. Now, keep in mind also that these implementations are not complete, so there's a bunch of caveats. But we can actually take a look at the plot. So here I'm just using a package to plot the plot for all these times. Hopefully, it's all right. And again, you can always see like there's a bit of waiting time. That's just Julia having to apply a bunch of stuff. Now I can see just a comparison of my default mode, which here it uses LAPACK underneath and in particular it uses open glass. But then I can see each strategy that we tried is a straight improvement. So the default one was really terrible. The second was a bit better, but then once we had the inbound and especially the turbo, we got very close. Okay, so the really nice thing about this is that none of this was hard. For the most time, we just had to use a macro here and there, change the order of the loop. I would take a bet that optimizing C code in this way is a lot harder. So it's very impressive that using just a couple of packages and macros, we're able to get very close to the optimized standard implementation. So moral of the story, there's a lot of tools that let you optimize your code very easily. Every time just take a macro, put it in front of the loop, and voila, your code is faster. So sometimes there is a price to pay in how general your code is and how critical it might be. Remember, inbounds, right? You need to make sure that your code does not go out of your array, otherwise you have problems. But if you, so if you have an inbound someplace and you index them outside of the array, you get a second. But if you're running this on a cluster where really you want to be as fast as possible and you know that the indexes are correct, then it's fine. Okay, so we can move on a bit to about standard parallelism. So we've seen a bit of multi-threading already. So as a recap, so if you want to start Julia with threads, you do this. I think I forgot the equal here, but should be here. So you can give as many threads as your processor can. Then within the Julia process, you can check either the number of threads or the thread ID of your current process. Then if you want to run a loop over multiple threads, the easy way to do that is to do this. So threads.thread, so there's again a macro that you set in front of the loop for I in each index A. So maybe for those who weren't here on Tuesday, so each index is sort of a way to get the correct indices for a given array, and they're guaranteed to be correct. And the reason you might need to do this is because it's not always the case that an array starts at 1. So default arrays, their indices start at 1, but you can get arrays that don't. And it's a massive headache. In a bunch of places, it has been a massive headache for people. The code assuming that you could start at 1 times 1.length A, then you get a metric that doesn't go that way and you get problems. So the recommended way is using each index or some other functions. So here is just an example. I'm taking an array and I'm writing the thread ID of each function in that place. So then at the end, AI would have just 1, 2, or 4, etc., depending on the thread that floats at that point. Again, you can check the manual. You should be careful, although, if you want to use multi-threading for some kind of reduced computation, for example, to compute the sum. So let's say you have this function that's single-threaded, takes a matrix, so an array A, or a matrix array, and it takes the sum of all the elements in it. So that's just the single-threaded version. If you were to try this one, this would not work because because S, right, it's a shared variable across all threads, and so we get a race condition with one trying to update, multiple threads trying to update the variables at the same point. So this will not work. The correct way to do this would be this. It's a bit more complicated. So first, what you do is take your array or iterator A, and you partition it. So you basically cut it into chunks. That's what it does. Iterator partition just takes a collection and takes multiple chunks. And here it's taking length A divided. So this is just a symbol for integer division by the number of threads. So it's cutting up A equally among each thread. And it gives a bunch of chunks. And then what you do is you apply for each thread, you give it a chunk of this memory. and you launch a threaded process on that. In this case, you run the thread sum single, so each thread will get a chunk of the array. It will run the sum function, and then once you're done, you gain the result, and then take the sum of that. This was a bit more involved, but really the manual is a bit clearer and more verbose about that. Okay, so now is the slightly more interesting topic, so distributed computing. So in exactly the same way as you can create launch Julia with multiple threads, you can also launch Julia with multiple processors. The cluster, or even on my laptop, we can. So for example, if I start Julia with cache P4, I want 4 processors available to Julia. But I can also do that at runtime. I can do this first step, loading the distributed package. So that's just the library, the standard library for all things distributed computing. And then I can call the add procs function, which is try to add processors. Here I can tell it, please give me 4 processors. I think if you don't give it an argument, you try to take all the processors for it. Okay, so again, we get in the notebook with this. But for the low-level API, in this case, for example, say you want to call a specific function at a specific processor with a specific argument, we do something like this. So R, if you remote call, and remote call takes a function, the name of a processor, so here 2, so I want to run this on the second processor, and then I give it the arguments of my function. So actually this is incorrect. I should remove the parentheses here. But at the end of the day, what this is going to do is go in processor 2 and call rand, so random number function, 2, 2, and so there should be a 2, 2 matrix. Okay. Now when I do this, we'll see in just a minute how it works. I don't get the result immediately. I get just yet an object that's a tutor should tell me, okay, whenever you want, you can get the result of this, but otherwise it's in the air. And then I can do operation with that. So let's say now what do S is equal to 1. So add 1 to each element of my matrix R. I can do that with spawn add. So this creates a new task at processor 2. Then it executes this expression here. So 1 dot plus, so add 1 to each element. Then I need the actual value R. No, so now it's fetch R to get the result of this. Then you can get the value of S. Then if you don't care about what processor your task is being run on, you can put any here instead of a specific number. But this part will be much clearer if I go to the notebook. There. I'll start by loading a few packages, but we won't be using them immediately, except the distributed one. So I can do, as I said, I can tell distributed to give me some processors. So please give me 4. And hopefully it should give me 4 processors with the indices. Here, we now have 4 processors available. Notice that there's actually always another one, but that's the default. So these are the 4 working processors I have available. So if I now call remote call, here I remove the parentheses. Okay, I get something future, right? So it's a complicated object. Basically just an object that can call fetch later to get the actual result. And this is to handle the fact that this might be working with either multiple processors on a single machine or multiple processors on a cluster. So maybe there's some latency involved. So I don't want the necessary result immediately. When I do, I use the fetch function. try that now. If I do format, so I create a new task, one dot plus fetch R, so add one to each element of R. Again, this is a future object. Now I can actually fetch the value of S. And it gives me, okay, it's a 2 by 2 matrix. And I've added one to each of these resulting plans. Sounds good. Then this is just starting a process. I don't really care about where I do that. Again, I can fetch value. That's more of the low level API. It's there, but there's a lot more options. So if we go a bit deeper, so first, sometimes you might want a function or some code to be defined on every process. So the standard way is to use the everywhere macro, basically evaluates the expression on each processor. This is useful for here. I'm just defining a new function. So now the function norm2, the squared norm of an array, is available on each processor. You can also everywhere using a package or include a file. So if you want some dependencies to be available everywhere, you should use this. Now let's try and take this loop here. So there's a serial loop. And I'm doing the basic Monte Carlo estimated phi. So sampling a bunch of points in pairs of points in 0, 1, 0, 1. If the norm is smaller than 1, I add it to a counter, and that should, if I take enough points, give me an approximation of phi. Okay, so here really it's a kind of MapReduce operation because I'm basically doing a sum or applying a function and then summing the result of these functions. So there's a really nice way to do that going with distributed macro. So again, you put a macro in front of a loop. And here it's a bit particular because it's distributed in plus, so that means compute the sum. So use plus as of a fold on the whatever goes on in that loop. What it's going to do is it's going to loop from 1 to n. It's going to compute whatever is inside the loop. So here I'm taking a random pair of random numbers, checking if the square norm is more than 1, then taking that to be an integer, and then summing that. And give me also a result. The actual time here is maybe not relevant because it's a very simple program. So for more complicated tasks, we would see a difference. Okay. So that's one very easy way. You can also use external variables. So let's say I have an array of random numbers and that's simply the sum of all of them. I can pull that in the loop and that goes fine. The only caveat is that this has to be read-only. So if I wanted to modify A, we need to do something special, but we'll see that in a minute. Finally, if you want to do, you have an array of inputs, and you want to apply a function to each input and get a result in an array, and you want to do that in parallel, that you use the pmap function. So map is just the function, so apply a function to each item in the collection. Pmap does that in parallel. So here, function notice that here I'm defining function again everywhere because I want it available on every processor. And here is my theory function, the coolest function, basically taking the number of times it takes for a given number to go back to 1 in the sequence. Okay, now I can map pmap code at length on 1 to 1,000. And you apply this function in this fashion to each of these 1 to 1,000. And I get the result at the end. So far, so good. Now, the last thing I have to say for now about distributed loops is if you want to modify an array, There's again another gotcha, same thing with views. So let's try this loop. So I define A to be 0, and I want to assign elements to my array using a distributed loop. But if you do that, actually the actual array does not get modified. The reason is that when the loop splits over distributed processors, each processor gets its own copy of the array. So the actual original array does not get modified, same thing as with views. So there's a similar solution for that. We want an array that's shared across all processors, and so that for that we use what's called a shared array, using the shared arrays package. And so if we do this instead, so A is now a shared array, so it's shared across all processors that are in this loop now. You have that each processor has modified the actual array. These are things to keep in mind. There's also another package that's defining distributed arrays, or arrays distributed over multiple processors and maybe multiple servers or multiple machines. So for, like, you have a really big problem that does not fit into a single computer, you might want to use that. Okay, let's go a bit later. Again, Daniel will have a lot of information about this. We've talked about all this. But yeah, another nice thing, if you want to start a program, maybe in a batch job, and you know already the dependencies, so you'd be, okay, Julia -p, the number of processors you want, and then -l for each dependency. So -l file 1, -l file 2, saying, okay, please include the contents of file 1 and file 2 for each processor, and then at the end, you take your main.jl, so that would be your main program. Okay, in this. So I have a little bit of, before going on to the actual packages for HPC, I have a bit of a intermezzo on using multiple dispatch to do some clever things. So it might be very common if you're writing a library, for example, that you have multiple either algorithm or multiple versions of an algorithm to solve the same problem. Like maybe you have this function foo single, that's the single-threaded version that should be able to run everywhere. But then maybe I want also a version that runs threaded, and maybe a version that runs distributed, and so on. And you want to be able to switch easily between these two, these implementations. So there's actually a very nice way to do this using multiple dispatch, which is to define, so let's say your high-level function would be called foo, and you can create these dummy objects. So you can create foo single, foo threaded, foo distributed. So these are just empty types that represent the different like algorithm that I want to use. Then my high-level function will be foo n. And then I pass it to, I define it as foo hold n with, by default, foo single. So the default behavior should be the single threaded. But then if the user wants to use the distributed or the foo threaded, the only thing that they have to do is call foo with 2 arguments and choose the algorithm that they want. So it's more of a nice way to organize a code or a library that we have a single function, and then depending on what the user wants to do, they just add a little type at the end. It's very useful because it means you could also do that dynamically. Maybe you just have a script and you don't know necessarily where it's going to run single-threaded, distributed threaded, but that's just an option that's passed, and so you don't need to even modify the script at this point. That's the sort of high-level strategy you can apply with multiple dispatch. I guess I see it's so 15:40. Maybe should take a little break. At least I need to get some drink. So yeah, back in a couple of minutes. C'est le mail pour le groupe Linux Inamur. J'ai reçu un mail hier du groupe Inamur sur l'utilisateur Linux Inamur.
Ah oui.
Irréductible gaulois, je vois. Ils ont créé une équipe Teams. Pour les utilisateurs Linux qui refusent absolument d'utiliser Windows.
Pardon?
En gros, apparemment, pour les gens Inamur qui refusent absolument d'utiliser Windows.
Moi, je suis pas sur Windows.
Je résiste encore et toujours.
Faut soigner de mon mercredi de Microsoft. Je passe mon âge, c'est pas possible.
Okay, so let's start again. So we've seen how to optimize geometry, how to perform it, how to analyze it a little bit. We also see how to use the standard library for distributed computing. Now we'll look at a few packages for going beyond that. So here it will be a bit more loose, but again, I'll go through a notebook of examples. So one package you might want to go to after using distributed is a package called dagger.jl. You can find the link on the bottom here. So Dagger, it's really nice because you could really think of a bit about an upgrade of the distributed. Because it's a package that lets you work with multiple cores, multiple servers, even multiple devices. So you can even use GPUs as well as CPUs. And I'm only really covering one thing, but there's a lot of things in here. But one thing that Dagger can do that's the threads cannot do is parallelizing multiple nested loops. So I have an example here. So basically, I'm doing an everywhere block. So don't really worry about this, but it's sort of a dummy example where I'm taking functions fi and gi, j, y. And there are just basically two dummy functions that are going to take different speeds. So I'm arbitrarily saying that they take some random time to run. So f is just going to be some amount of time, and g is also going to be some amount of time depending on the result of fi. So now, if I have this nested loop here, so I have a function, and on the top I have an auto loop at sync for I 20, and then I have a first statement. So I spawn a process for computing f of I. So dagger.spawn is a bit like the threads.spawn. So this is going to launch a process to compute f of I in some processor. And then after that, I have a second loop, an inner loop, that is going to spawn a second process for computing G. And notice that this process depends on the output of this process. So if you were just using something like distributed, you wouldn't really be able to parallelize this both loops at the same time. So you could either run the first loop in parallel or a second loop. But Dagger is smart enough to figure out how to do both at the same time. So I think I've got a better example in the notebook, but so wrong. So yeah, really, I'm not saying a lot about Dagger, but you should definitely check it out because it's a very powerful, although still in development in some parts. But you can do stuff like load a file, a very large file across multiple processes, and you don't even need to load the entire file in memory. You can do that lazily. So you can do some very smart things. So another package which is also worth checking out is it's a more functional style of doing parallel computing using what's called transducers and folds. So the rough idea, let's say I have this example. I take all the number from 1 to n might be very big, and I want to do some complex operation on that stream of numbers. Like first, I want to only take prime numbers. So let's say I have a function is prime that returns true if a number is prime and false or not. And then I can use the filter. If you've done any functional programming, this would be familiar. But filter here, smart because it's going to take this input here, and this triangle here is called it's the broadcast, not the broadcast, the type operator. So it takes what's on the left and feeds it to the input of this. And then the result of this is fed into the input of this, and so on. And so this filter is prime is going to take a stream of numbers and only spit out the ones that are prime. Then it goes on to the next one. And there's some interesting stuff. So then I can do another filter. And I want palindromic prime. So primes, that's when I write them in decimal, and I swap the order of the digits. It's the same. So it's an arbitrary example, but you imagine doing multiple operation like this. So first I want only the prime numbers, then only the palindromic numbers. And then I just want to count them. So I'm first applying a map, mapping some n to 1. So this is a lambda expression that takes, so n is the parameter, and the arrow here, it's rendered a bit weird on my slide, but in Julia it's just dash greater than. So it maps each into one, and then it takes the sum of that. So at the end, I get the count of all the what's left after this. And the nice thing is that all of this expression is going, by default, it's going to run in multi-threaded mode, but it's going to be smart because as I mentioned, it's a functional style of programming, which means that it won't be, okay, first take one-to-one, go to the filter, and do all of that first, and then go through the second filter, do all that first. It will do that step by step. So actually, it will be fairly efficient because it won't do one operation completely, then the second operation completely, and so on. It will do them one by one. Another way to do the same computation using the transducers package. Because we're taking a sum in terms of functional programming, is what's called a fold. So here, a fold D for distributed. It's a special fold. The fold operation is sum, so it's the same idea that distributed plus and then a loop. And then I give it an iterator, so 1 for n in 1 to n, if is prime n is prime n. So this is similar to the array comparisons I mentioned in the first part, but probably this is essentially equivalent to this, but this will run in distributed mode natively. So sometimes, maybe in other ways, but you can sometimes express complex computation very easy in this style. And because the compiler is very smart, it can do that efficiently. There's no dead weight from that. The last few slides are more about going further, but I don't have examples for this, but I'll still finish up with a nice example. So if you want to run your code on a GPU, which is getting more and more common nowadays, especially for trying to do machine learning, well, the good news is that there is a bunch of dedicated packages for running Julia code on GPU. The best supported one is CUDA.jl. Learned that on NVIDIA GPUs. It was one of the first ones that was fully featured, and it lets you run Julia natively on Julia on NVIDIA GPUs. It then took a bit more time, and some of these are not completely done yet, but they're getting there for other packages. So one API for Intel GPUs, AMD GPUs, and if you want to run stuff on a Mac, you can also do that. Then there's some also high-level libraries for what's called ISAM operations. So if you have complicated array operations, you should maybe look at Tulio, and Tulio is going to do stuff like using this loop vectorization and different tricks for loops. And on the right here, I have an example of how to define a CUDA kernel. So remember, the GPU define a small function that takes a smaller part of your inputs, and then that function gets run massively parallel. And so it's actually very similar to the way you use CUDA in a C++ way. There's types for block ITX and so on. So it's a bit verbose and not super intuitive, but at least you can write for kernels directly in Julia, and they'll be just as fast as if you had defined them in C++. But maybe you don't want your code to run only on CUDA GPUs. So there's a really nice package for that. It's called kernel abstractions, which actually lets you define kernel for a GPU, but in a backend agnostic way. So what that means is that you define a kernel function, and then you give it like a backend. This could be CUDA, this could be ROCm, also any GPU backend you might want. And it's going to automatically generate the correct kernel code for you. So on the left here, I'm defining the kernel for a matrix multiplication. And it's sort of unified or simplified version we had on the previous slide. So first I get the index. And, okay. You can check the documentation for what all of this means, but and I think this is a matrix multiplication kernel that's going to be valid for any of those libraries here. So I could define this. Then, depending on my machine, if I have a CUDA GPU or something else, I can just get this part here. So that is backend kernel from the get backend. So this will tell me, okay, in this particular machine, what is the actual GPU that we have? Get the correct computed code for that. Normalement, le local ici est réservé jusqu'à 17 heures. Normalement, ici, le local est réservé jusqu'à 17 heures.
C'est systématique dans les cycles qui suivent.
Oui, mais pour moi, c'est le local est réservé. Non. On plus de. Mais il y a encore un notebook à voir. Mais...
J'ai l'impression qu'il est resté peut-être toute la journée.
Oui, donc on a raison, donc on peut rester. De toute façon, ils vont l'air de se.
08, c'est celui qui est réservé.
Oui, mais je crois que souvent, en fait, les gens ne réservent pas ou ne font pas attention à ça. Donc ici, on est en droit de rester. Okay, so we don't have to get out just yet. So the nice thing is that this function will be valid whether I have a CUDA GPU or anything else. Because it's a, remember I showed you this strategy of switching between different implementations. This is the same idea at play here. It's specializing depending on whether it's a CUDA backend or whatever. So this is nice because your code now does not really depend on an actual specific GPU vendor. You can switch easily. So the documentation is pretty nice. There's also a nice blog post on the bottom here by some guys that wrote a fluid simulation over. They started from a single-threaded one, and they rewrote it using kernel abstraction to be able to run it on GPU in a package agnostic way. So this might be a more nice example if you want a practical example of people doing this. GPU is probably as easy as it's going to be to define GPU kernels. If you don't want to learn C++ for that, maybe you should try it. So I'll just finish with some honorable mentions. So I haven't mentioned it, but there is a package for MPI called MPI.jl. So if you want, it gives you a full implementation of MPI. Although in some sense, the default distributed also works a bit like MPI, but it's not quite MPI. But if you want full MPI, you can. The second package, it's really nice, but I haven't been able to make it work on the cluster, and I think why. I think I know why. So in principle, it lets you run like jobs from a cluster manager, including Slurm, which is what we use on the clusters here. I think the reason it won't work on Hercules, for example, is that it assumes that you have srun. You're allowed to call srun instead of sbatch. I don't think users have that privilege by default. You have to use sbatch, and so that's not supported in this package. But in principle, it might be. Some other two ones. So this third one is more if you want to do a scientific project. It's called Dr. Watson. It's not specifically for high performance computing, but if you want to do some kind of scientific project where maybe you're running simulation and then saving them to files, this basically helps you do a lot of also both the bookkeeping and the boilerplate for that. So you generate nice file structures. it will give you files from the simulation that gives the results. Then you can recover them in a nice structured way. So it's more helpful thing to have, but not necessary. And then that last one, that's another like evil optimization trick. So I mentioned that the default like linear algebra use open glass, but you don't have to use that. You can actually use any blast you want. And you can even change the blast implementation, so the LAPACK implementation, dynamically at runtime. So if you have a specific library for your processors that's very optimized, you can use that. And that's using this library called libblast trampoline. So it's very specific tools that give you like very specific control over what exactly gets used, but it's made super easy. At the end of the slide, I have one more notebook to cover. The second part of this one. So here I'm basically running the same example for Dagger as I have in the slides. That for nested Dagger. When I tried it, it was actually a bit slower than. Oops. I think I forgot. Let's see if this works. Ignore the message. Now this should work. This should take a little bit of time, but let's look at what you could be able to do using the just plain distributed. So I only mentioned that distributed can only apply to a single loop. So here you have to choose between the outer or the inner loop. But actually, when I tried this, like running this loop was still a bit faster. It's taking some time, so it's moving on to the rest. Yeah. You mean taking a collection of all the inputs? Yeah. Yeah, that's something you could do. One problem you might run into is that you have a very large array. Like it might not always possible to do that without allocating memory for all these inputs, but that's one strategy. And I think that's, remember I mentioned Dr. Watson, that's one thing they do to generate like all the inputs you want, combination of inputs, and then it generates a big vector of all the inputs, and then you send that to do that. It's going to take some time. So. We'll have to wait for it to complete. Didn't take as much time when I tried first, so maybe it's not something about something. try to improve the solution. So just shut the notebook. So this do that again. So I'll just have to go back to the top. The nice thing about this example, they show you that the startup time sometimes can be very long. Usually gets better when you've loaded the precompiled library first, but sometimes some stuff can take some time when you restart a new process. But to the end, ignore this example, focus on this last one. So here it was the idea of, okay, I'm taking prime numbers and only keeping them that are those that are palindromic. Don't really care about what this means mathematically, but let's go for it. So let's say I want to take n to be 10 to the 8. And now I'll run this line. So it's very short, but this by default will run only in multi-threaded. And because it only has one thread, this should be fairly slow. We'll wait for this to complete, but it shouldn't be too long, hopefully. And then the good news is that after that, will be done. But that in general, the pipe operator, it's not specific to these functions. You can use that in normal Java code. Sometimes it's nice because it really lets you express a complex operation as a fairly short line. Okay, 1 minute. Thankfully, I'm not benchmarking this, otherwise we'd be here for a while. So I'll try shutting for the programs to see if that will be faster. Okay, finished. Okay, 2 minutes, so wasn't the fastest. Then if we run the second one, so this one runs distributed, so it should be a bit faster. Maybe you can even pitch up to the CPU. You can see that yeah, 4 processors running at about 1%. So those presumably the one allocated to this process. for record, last time I tried this, it was about, I think it was less than a minute. So, okay, it was exactly less than a minute. So notice that we used 4 processors here, but it was about only half as fast. So not the greatest performance gain, but I think it's also because this function here is not super optimized. But just this was multiple example that you do have a lot of options for expressing compositions that don't necessarily use loops. And that's about it. Yeah, I have maybe one last example, but it's not about parallel computing. But I mentioned the other package for code Python. It's more that I have a node script that I wrote some time ago. It was interesting. Even if it's only 1622, you can have it. Do not judge the amount of tabs that I have. We close that so you cannot see. But so there's more examples. This is another notebook environment for Julia, but it's repeat Julia. The difference between Pluto and Jupyter is that Jupyter and the Pluto notebooks are reactive. So unlike a Jupyter notebook that has cells that you execute and the result is held, here it's a bit like in Excel when you can have the value of a cell depend on the value of another cell, and we update the first one, the second one updates. So this is what happens. So to give you a bit of a description of what's going on here, so this is another example of calling Python. Specifically, I'm doing some very evil stuff because I'm using the package PyCall to use this folium library. Now, the folium library is a Python wrapper around the JavaScript library to display some maps. So I'm calling JavaScript through Python, through Julia. And all of that, so I have like some OpenStreetMap data from the mirror. And basically, I'm getting some random points in the mirror, getting some like shortest paths, and then displaying them in the Python library. It's roughly so. But you can see that it works with some minimal glue. It's more interesting. I think you can still see the parts without Python. Yeah, so this FLN.python, that would be basically the Python code. But otherwise, like there's no problem running that in Julia. So the question is that the answer that you don't, like you have little control over what Python does. So that's one thing to keep in mind. So if you use some external library, the Julia compiler cannot optimize over it. So here, I think I'm not 100% certain. I think there's a Python process between interpreter that's run, but then, if I remember correctly, Python does have like an API for interacting with it. The same way that MATLAB also has a C API for creating MATLAB types. So so you're asking about getting Julia as an embedded language in maybe C++ or something? here, I think it's a Python interpreter. I think we can even configure to use your default Python environment or a local Python environment. Okay, so I have, I'm all stuff to show for. Thanks everyone for coming, even those that had to leave after the break. So, yeah, I don't know if everyone has more questions or maybe like some specific thing that you'd like to know about.